and welcome to the first Coffee Shop Astrophysics talk this semester. These are some events which are happening in the UWM Planetarium. If you are interested, you should check them out in this website. In case you are wondering who we are and what we do, we are a set of graduate students in the Leonard Parker Center for Gravitation, Cosmology and Astrophysics at the University of Wisconsin-Milwaukee. Okay, so today our speakers are Sarah and myself, Pratyusha. And if you have any questions or you have an idea for a future coffee shop talk, feel free to contact us at this email, or you can just come up and say what you would like to hear about. Now let's move to the topic of today's talk. For today's talk, we have some questions which kids often ask. Kids ask a lot of questions. Some of them are easy to answer, some of them are hard. We have not thought of some as adults, and very often they share a very different perspective of the world than the ways adults think about. So we have selected some questions which are related to physics and astrophysics, and some are very different to the ways we think as scientists, like why do stars float and what paints the sky blue in the mornings. So let's go on to our first question. Why do things fall down? So just before entering into this talk and answering this question, I just want to introduce what the word force exactly means in physics. We use the word force very often in our day-to-day lives. So these are two properties of bodies. If a body is at rest, like the laptop, it will always be at rest unless and until someone comes and move it. If a body is in motion, it will continue to move with the same speed. This might sound a bit counterintuitive because in our day-to-day lives we have friction, and friction is the force responsible for slowing a body down. And if you think about them deeply, both of these statements are exactly the same. So let's say if I have some superpower and I can shut all the windows and start moving anodyne at some constant speed towards the lake, then there is no experiment or no way which you can say that if this coffee shop is moving or it's at rest. The same thing happens when we are moving in an aeroplane and there is no turbulence. So inside the aeroplane, it looks like everything is at rest, while for someone who is on the surface of Earth, he or she sees that the aeroplane is moving. So to define rest or motion, it has to be with respect to someone sitting at some frame. So these two statements are actually the same. And a force is something that changes the state of motion of a body. Like if I move this laptop, or if I accelerate, or if I slow down, then I require a force. And this is Newton's first law. Okay, now let's come back to the question which we were trying to answer. Why do things fall down? Or we can phrase it in a different way as why does everything get attracted towards the surface of Earth? The answer, so here it's not really falling down, it's just we are glued to the surface of Earth and things move towards the center of Earth. And the reason why we see this is gravity. So gravity is a force which causes every object in the universe to attract each other. Now this force of attraction increases with the increase in mass, and in our day-to-day lives, we only feel the Earth's gravity because the Earth is very massive. So if you compare the mass of Earth to the mass of elephant, how many elephants do you think that we need to balance the Earth? Any guesses from the audience? Like any number? Okay, so we have 1,000,000 and a trillion. So this is the answer. So it's way more than 1,000,000. And trillion is a nearer guess. So we have 21 zeros. So it's 1,000 billion billion. So if we have 1 followed by 21 zeros number of elephants, then that would be equal to the mass of Earth. So the Earth is very massive. And since the Earth is very massive, we can feel Earth's gravity, and that actually pulls everything towards the Earth. And that's why we are glued to the surface of Earth. If I drop something, it falls down towards the surface of Earth. Okay, so this answers our first question. So let's go to the next. So if the Earth attracts everything to itself, why does the moon not crash into the Earth? Or the satellites which orbit Earth, why they don't crash into it? So this is just a picture of the moon crashing into Earth. The reason has to do with trajectories. So if I throw something, here it covers a horizontal distance, and we tell that distance to be the range. Now, if I increase the force or the velocity by which I am throwing an object, the range increases. Now, there is some very special velocity. If we throw an object at that velocity, it follows a special trajectory which we call the orbit. At this trajectory, it always falls towards the Earth. It always tries to touch the surface of Earth, but it always misses. So these orbits are known as a trajectory. The moon is in one such trajectory, so the moon is always falling towards the surface of Earth, but the trajectory is such that it can never touch the surface of Earth. So it starts to orbit around the Earth. While launching satellites for our communication and day-to-day activities, we also launch it in one orbit so that it goes around the surface of Earth. And if we want to leave Earth's gravitational pull, we need to increase the velocity further, and that velocity is known as the escape velocity while launching rockets or some stuff like that. Okay, so to answer this, the moon is actually falling towards the Earth, but it's always missing it, and it will continue to fall but never touch the surface of Earth. Okay, so the next question, why do stars float? So if we look up at the night sky, it looks as if stars are floating in some medium. And if you are wondering, the density of stars is very close to density of water, so it can float in several liquids. And this is a picture from the Headlands Dark Sky Park. Why we don't see this when we look up the sky in Milwaukee is due to light pollution. We have lights from our homes, from our cars, from the streets, and that light is too bright to see these stars. So why do they float? Well, stars are actually not floating. So the star which is nearest to us is the sun, and the sun actually moves around in a galaxy, and the sun drags all the planets with it. The sun moves around the central black hole, which is a very compact, massive object. It weighs around 1 million suns, and the sun falls around the central black hole just in the same way the moon falls around the Earth. So the sun orbits the central black hole of our galaxy, which is called the Sagittarius A, and just a few months back, I think all of you saw pictures of Sagittarius A, like in radio, like it was the second direct image of a black hole by the Event Horizon Telescope. And as the sun orbits around the central black hole, it drags us with it. So the Earth is orbiting the sun, and the sun is orbiting the central black hole, and we also orbit the central black hole with the sun. Now this is how the sun moves around our galaxy. It takes 230 million years for the sun to come back at the same place, and its velocity is 137 miles per second. This is a very high speed. If you could drive in this speed, then you would reach, let's say, Washington, D.C. in just 5 seconds from Milwaukee. So this is very high. And this is the image of some stars around around the center of our galaxy. So this is like This is observed by the Keck telescope for 23 years using a group at UCLA, and Andrea Ghez was the leader of that group, and she was awarded the Nobel Prize along with Reinhard Genzel and Roger Penrose in 2020. So Reinhard Genzel and Andrea Ghez was awarded the Nobel Prize because this was the first evidence that we have something very massive at the center of our galaxy, and that has to be a black hole. Roger Penrose shared the Nobel Prize with them because he was the first to show that black holes are actually a solution of Einstein's general relativity. It's not some mathematical artifact or some weird stuff in math and that comes out, and that doesn't exist in reality. So to sum this up, why stars float? So a star is way more massive than Earth. A star weighs around 1 million Earths, and so there is no reason that it will crash into the Earth or the Earth can pull a star towards itself. The motion of stars that we see, the dominant reason is due to the rotation of Earth, and other motions because the sun is moving around the central black hole and all other stars are also moving around the central black hole. They are very tiny because they are far away from us. If an object is far away from us, it's very difficult to figure out if it's moving or not. And the easiest way to understand that stars move is if you look at the pole star, like the star which points us towards the North Pole, and it is still used for navigation, like you figure out where the Polaris is, and then you know, well, that side is the north. But the pole star changes with time. 1,000 years from today, we will have a different pole star, and 1,000 years ago, we also had some different pole stars. So this is just a screenshot from Wikipedia which shows what will be the pole star and what was the pole star at past. Okay, so why do stars float? They don't. They fall towards a central black hole in the galaxy. And the reason we don't notice it is because they are very far from us, and it's very difficult to figure out if things which are far away and they move. Okay, now the next question, and which I used to wonder as a kid, like wherever I used to go at night, it appears that the moon used to follow us, like we can see the moon from everywhere at night. So why does it appear that the moon is following us? Well, the answer is very simple. It's very far away from us. So how far is the moon from us? To get a perspective, this is anodyne during our last coffee shop talk. And this is roughly 30 feet, I guess. And if I zoom 1600 times, then we get more or less the downtown Milwaukee, which is around 6 miles in this diagram, and 6 miles is 32,000 feet. And now it's a good idea to change to miles, because had I been using feet, then I had to add zeros after zeros, and too many zeros makes things confusing. So if I zoom out 500 times, then we get more or less the entire United States, and the breadth of United States is around 3,000 miles. Now let's zoom out further. Zooming out 18 times, we get the Earth, and the radius of Earth is 8,000 miles. Now you might be wondering that 3,000 into 18 is no way 8,000. The reason why the radius of Earth is 8,000 miles is because when I'm talking about the breadth of United States, I am measuring on the surface of a sphere. So let's say you have a ball and you wrap a string around it. Then if you open the string is much longer than the radius of the ball. So if we measure distances on the surface of Earth, they will be longer than the radius. Like the radius is just cutting a tube across this sphere, or this is the diameter. So the diameter of the Earth is 8,000 miles, and if you measure the breadth of United States along the surface of Earth, that will come out to be 3,000 miles. So that's why those two numbers didn't match. Now let's zoom out 30 times more from this. And now we can see our moon, which is at a distance of 240,000 miles away from us. And since it's so far away, we can see the moon from this half of the earth where it's night. And in our day-to-day lives, we don't move this much. Like we move around this tiny dot, like around our place. And since we can see the moon from this entire region, it appears that the moon is always following us wherever we go. Okay, now just to summarize this question, the reason why it appears that the moon is following us at night has to do with the distance. The moon is far away from us, and so we can see it from a wide region. Okay. So the next question is, how big is the sky, or where does the sky end? Now, to answer this question, we first have to figure out what do we mean by the sky. And here I am going to say what we have in our universe and the structures that exist in our universe. So this is the Earth-Moon system, which I showed a couple of slides ago, and this was 240,000 miles. Now let's zoom out 31,000 times, and then we get the entire solar system. Now, not the entire solar system, like the sun and all the planets. Now, this is at a distance of 7.5 billion miles, and again, this has too many zeros, which becomes difficult to keep track of. So we change the units to a unit which astronomers often use, and that's known as the astronomical unit, or AU in short. Now, 1 AU is 100 million miles, and the distance from the Earth to the Sun is actually 1 AU. Now, if I zoom out further 3,400 times, we get the nearest star. So, the nearest star is very far away from us. It's Proxima Centauri. It's at a distance of 270,000 astronomical units. That means the distance from Sun to Proxima Centauri is 270,000 times the distance from Sun to Earth, and so stars are very far away, and that's why it's very difficult to see how much they are moving. If I zoom out 5 more times, then I get all the stars in the solar neighborhood. There are 20 such stars here. And now again, astronomical units is not a very good scale to measure things. And we switch to light years. What we mean by a light year is the amount of time light can travel in 1 year. And 1 light year is around 63,000 astronomical units. Now we can zoom out further. We zoom out 3,300 times, and we get our entire galaxy. Now we are somewhere here, and this star is not at all to scale. We and all the planets in our solar system are just one tiny dot at one of the arms of our galaxy, and the diameter of our galaxy is around 100,000 light years. Now, some properties of our galaxies. We call our galaxies the Milky Way, and it's a spiral galaxy. It has spiral arms, as you can see, and the age of our galaxy is 13.6 billion years. We have 100 billion stars in our galaxy, and our sun is a very typical star. So, if we have 100 billion stars, we would expect the mass of our galaxy to be 100 billion times the mass of our sun. But when we actually measured the mass of our galaxy, it turned out to be at least 10 times more massive than this. And it's around 1 trillion solar mass. So there is something in our galaxy which we can't see. And since we can't see them, we call that dark matter. And our galaxy is mostly filled with dark matter. And it's not luminous. We can't see it. So this is looking into the Milky Way and it appears a bit milky, and that's how our galaxy got the name of the Milky Way. And this is looking into the disk of the Milky Way, and this is out of the disk of the Milky Way. Okay, now we can zoom out further, and I'm going to use this video for that. So this is our galaxy, which is a spiral galaxy. All galaxies in our universe are not spiral. We have elliptical galaxies. We have some galaxies which have weird shapes. And these are some galaxies near us. All these galaxies form a group, and since it's near us, we call them the local group. And these are the galaxies in our local group, and they are very far away from us. Several local groups form the local supercluster, and these are the groups forming our local supercluster. And there are several superclusters. If we keep track of all superclusters and try to make a map of our universe, we will see some filamentary structures like this. There's places with overdensity of matter, and there are places where there is nothing. These places are known as voids. And this is the farthest visible universe. Like, our universe is not infinitely old, and light takes some time to come to us, so we can't see everything. There is a horizon of our universe, and the horizon to our observable universe is 46.5 billion light years, or it's this many miles. I think it's like 27 followed by this many zeros. I forgot how many zeros we had here. Okay, so this is the size of our observable universe. So we have several stars. We have 100 million stars in our galaxy. So why at all is the night sky dark? The idea is that if we look into the sky, we will always hit the surface of a sky, the surface of a stars, and stars are bright. So the night sky should be completely filled with stars. And the reason why we don't see the entire night sky filled with stars, which I used to think for a long time, is that stars are very far away, and if we have a light source far away, it appears less bright. We see that in our day-to-day lives. But this explanation actually doesn't hold. The reason being that if we look farther and farther into the space, we can see a larger and larger area. Now, if we can see a larger and larger area, then we will have more stars in that area. And the fact that as we look further in space, things become less bright, and the fact that we see more of these sources, they actually cancel each other. And we should expect that the night sky to be bright. And this was a paradox which existed for several years, and it's known as the Olbers paradox. Although this paradox existed at least 100 years before he was born, but for some reason it's known as the Olbers paradox. I am not sure why. And the model of the universe that we had then was primarily due to Newton, which said that our universe is eternal and unchanging. Like, the universe is same and it was the same always. We call that static. It's the same everywhere and in all directions. So how far we look back in space, we see exactly the same structures. Whichever direction we look in space, we see the same structures. So this was the model of universe back then. And if you have this model of universe, you can show that the night sky should be as bright as the surface of the sun. And this was a paradox that existed for several years. And the way to resolve this, the problems were in this model of the universe. We today know that the universe has a finite age and it did not exist the same way, and light takes finite time to come from stars to us, so we can't see everything. We have a horizon, and the universe is also expanding. Since the universe is expanding, the wavelength of light increases and we can only see a very narrow range of light. Like if the wavelength increases, from visible it becomes ultraviolet, sorry, from visible it becomes infrared and microwave. So we can't see microwave and infrared light. And also, like, it's not the same everywhere. We have structures in our universe. We have the galactic plane where there is a lot of dust and it's very difficult to see stars there. If we look out of the galactic plane, we can see the stars, but there are less stars outside the galactic plane. The universe is, if you look at cosmological scales, then it looks the same. Like it has the same distribution of galaxies everywhere, but in local scales, this does not hold. And that's how we resolve the Olbers paradox. The main problem with the Olbers paradox had to do with the model of universe that existed. Our universe is still young. It's 13.7 billion years old, and we can't see everything because the light has not reached us yet. So that's the answer to why so many stars don't light up the night sky. So the next question is, why do the sun and the moon move in the sky? So all of us have noticed that the sun rises from the lake and sets away from the lake. So the sun rises in the east and sets in the west, same for the moon, the same for the other stars. And the reason we see this motion has to do with the rotation of the earth. The earth rotates from west to east. So all celestial objects look that it's rising from the east and setting in the west. Okay, so the sun rises in the east, the moon rises in the east is mainly due to the rotation of the earth, and the earth is spinning from west to east, not east to west. Okay, the next question that I have is, why do water level in oceans rise and fall, or why do tides occur? So this is a picture of Hopewell Rocks at the Bay of Fundy in Canada. This is a picture of low tide, and during some times in the day, the water level rises up. So why at all does this happen? The reason has to do with the moon. The moon is much less massive than the Earth, but it's pretty massive. Like one Earth is roughly equal to 81.5 moon, and so the moon has some gravitational say in what will happen. And what the moon does is the moon pulls all the water towards itself, and so if we are facing the moon, then the water level will rise in this region where the moon is not directly overhead, then the water level falls. Now the water level also rises in this region, and why this happens is a bit complicated. The reason again has to do with the rotation of Earth. If we are in something that's accelerating or decelerating, let's say if we place the brakes on our car, then we tend to move forward. So in things which are accelerating, strange forces act, which we call the fictitious forces. One such fictitious force is the centrifugal force, and that's responsible for causing high tides in this region. Okay, so this is why tides happen. It's due to the moon's gravitational pull, and there are also effects due to the rotation of the Earth. Okay, now I hand it over to Sarah. I should switch this off.
I think, hello? Okay, I think it's working. Okay, so my first question is, why do stars twinkle? And I have this GIF here so we can remember what twinkling stars means, because we don't have a lot of stars here in Milwaukee. We need to stargaze in a place with less light. So it's always nice to remind what I mean by that. And from this GIF, it's not like a real picture from the sky, it's just an artistic envision. We can see that actually twinkling skies, it's something pretty to see. Stars just seems like those sparkling diamonds in the sky. And it even inspired like poems and kids songs. So we have Twinkle Twinkle Little Stars. The question is, why stars does that? And we may be tempted to think that it's because stars itself changes their brightness over time. And we know that some stars do. We have, for example, a class called Cepheid variables. And they have a variable luminosity over time. But the range that they change their luminosity is like from days to weeks. And we see this twinkling like it's almost an immediate thing. It's not something that takes days to change. So if it's not the stars themselves, what causes it? And it's atmosphere. And before explaining how atmosphere does that, I want you to remember or learn now what is refraction. So if you have seen this before, it's just a recap, but if you haven't, I will explain right now. So refraction is when the light passes from one media to the other. So we can imagine that this white part is like air, and this blue part is like a layer of glass. And when we have refraction, this ray changes the angle here. And this happens in the atmosphere. And you may ask me, but the atmosphere is just like this giant layer of oxygen and nitrogen mostly. So there's no different layers there. But what happens is that when you have different temperatures, so you have pockets of hot air and pockets of cold air in the atmosphere, they act like different lenses, different layers. And they will refract light. And light will just like, and the light of the stars will just seem wobbly when we observe on the Earth because those layers of hot and cold air also changes over time. So every time we see the star, the angle that we are observing it, it's slightly different. And it just seems like a wobbly thing. And this is the reason why stars twinkle, and it's actually a very bad thing for astronomers. It's pretty to observe in the sky, but imagine you're trying to observe a star, and every time it changes direction. And there's a reason why Hubble telescope was for so many decades the best optical telescope in the sky. And what about ground-based telescopes? How we can use them and make them be as good as those optical telescopes that are space-based like Hubble? And the answer for that is lasers. So actually we have a solution for that right now. And what this laser does is cast this laser into the upper parts of the Earth atmosphere, so in the mesosphere, and it energizes an atom. And this atom in the mesosphere, so in the very high end of atmosphere, acts like a star. And we know what we would be expecting to see from this artificial star that we create. And we can compare to what we are really observing in the telescope. So what we do is that we distort the mirrors, the lenses in the telescope, so we can overcompensate this. And then we can observe stars with more quality. And I have an example of this. So in this picture here, we have Neptune. So it's not a star, but this effect can also be in planets. And we see that we don't use this technique. This is like this image that we saw. And when we use this technique, we get a much more better image. So just to finalize, why stars twinkle? It's because of the refraction of light that happens in the atmosphere. It's not something good for astronomers, but it's really pretty if you want to see them. And the second question is, how do mirages happen? It wasn't an original question, it was a side note because the fact is the same, so I'm giving the answer is also refraction. But I decided to just redo it as a new question for itself. And here's a picture of a mirage. So it happens in like really cold and dry places like the deserts. And we can see that we think there's water in here because we see the reflection of the palm trees, those power lines, and we imagine if there's something like reflecting it in the ground, maybe it's because there's like a layer of liquid water there. But there is not. And the reason that happens is because, again, we have these different regions with cold and hot air, and light is refracted. So what happens is that, in this case, light is bent, and makes this red weird uh, direction here that we are seeing. And because our eyes tends to think that if we are seeing light, they came in a straight line, light actually made this direction here, but we thought it made this one. So we imagine there's like a mirror here, like a body of water that is mirroring the image that we are seeing directly. So how do mirages happen? And the answer is, as I said, refraction. One more time. And now I will talk about why is the sky blue. And we have a picture here just to show it. And I'll tell what I think when I was a kid, because I have an answer for this when I was a kid, and it was completely wrong. For me, because I always saw like artistic visions of the night sky being dark blue, not black, as it really is. For me, the night sky was dark blue. And what happened during the day was that the sun would cast light in this dark blue shade, and it would become light blue. But this is not the reason that the night sky is not dark blue. And the reason why the day is blue, it happens because of the atmosphere too. But before explaining that, I'm just going to talk a bit about light because it helps us understand what's happening. So this is the black body that the sun emits. It's like all the wavelengths that sun emits, and we can see that the brightest ones are visible light. And when all the colors of the visible light, so red, orange, yellow, green, blue, violet, are together, packed together, we see white light. So white light is just the combination of all the colors together. But when they are separate, we see them here separated. And the difference between each one of the colors is just the wavelength. So for red color, we see that has a greater wavelength, so it's less energetic. And for the blue color, it's more energetic and has a smaller wavelength. And the reason why we see the sky as blue is because the blue light is more scattered in the atmosphere. So we have some molecules in the atmosphere, mostly nitrogen and oxygen. And what happens is that they scatter more blue light than the other colors. So the other colors kind of stay together in this almost white light ray because now they lost the blue. But the blue light kind of separates it, and it shades, like it paints the sky as blue. One interesting thing that we can see here in this picture is that also like violet being scattered, and what happens is that blue and violet colors are more scattered than others. But the problem is we don't see the sky as like blue-violet-ish shade. So why is that? It's basically because of our eyes. So more blue light is scattered, but a bit of violet is also. But our eyes are not as good as detecting violet. Violet is the very last color that we can detect, and we are not as good as detecting it. So there's like two answers for that. One is blue light is more scattered, but we have an eye limitation too. Otherwise, we probably would see a more violet-ish color in the sky. And just to finish this topic, I just wanted to say some curiosity. Actually, the day in Mars is not blue. The sky in Mars is kind of red, orange color, and during sunset and sunrise in this part here, we see that the surroundings of the sun is blue. So it's the opposite, because our sky is blue and our sunset is red, but in Mars is the opposite. And this is because of the composition of Mars. Mars is mostly composed by carbon dioxide, and the wavelength that is scattered on Mars is different from ours. So just why the sky is blue? Because blue light is scattered in the atmosphere and separate from the others. And next question is why the sunset is red? Because I've just said that in Mars is blue, but in Earth is red. We know that. This we can see almost every day. But why this happens? And for this, we just need this picture. And what happens is that during midday, the amount of, the size that the light from the sun has to travel is smaller, because when it's sunset, like this distance here is greater. So it has to travel more atmosphere. So I've said that blue light is more scattered, but when we have this greater distance to travel, actually all lights are scattered. So what happens is that all of them kind of stay together, and the only light that remains unscattered from the sun is orange and red. So we see the sun as orange and red. And so we see the sun as red during sunset because it's the only unscattered shade during this time. And now we'll have two questions that will talk about transportation. So we'll have a ship and an airplane questions. And this first one is, how do ships float? And before explaining this, I just want to remind you about the Archimedes story. It seems like this is a myth. That's not how he discovered the Archimedes principle, but I decided to put it here because maybe you heard of it at some point in your life. So it seems that Archimedes was taking a bath, and he realizes that part of the water was being displaced in the ground. And the weight of the water that was being displaced on the ground, he realizes was... oh, I'm sorry for that. Was the force that was exerted on him. So the Archimedes principle says that the force exerted on a body that is immersed in a fluid is equal to the weight of the fluid that the body displaced. So for a ship to float, we needed that the gravity is overcompensated by the buoyant force. And this buoyant force, it's given by this formula. So what we need is that the force that the gravity is trying to push this float, like this amount of object down, has to be overcompensated by the buoyant force. And as I said, this buoyant force is equal to the force, like the weight of the water that has been displaced. So we see that we have this volume that is immersed and the density of fluid, so this would be the weight. And so the buoyant force is just the weight of this object times gravity. And this is because this is how ships float. It doesn't matter the weight of the ship, it just matters that we have to have a buoyant force that is equal than this, so the ship will float. And so ships float because the buoyant force compensates gravity. So it has to be equal or greater than gravity. And so with this, we can answer why airplanes fly, which seems a more difficult question, less obvious, something that we don't see in mechanics 101, so how? And the answer is pretty easy. I can answer in a slide. It's just magic. But it's not too much scientific, so I cannot use this one as an answer. I have to do a better job. And those are the forces that act on an airplane. So we have the weight, which is basically gravity, the lift, which has to compensate gravity, so it's like the buoyant force in this case. We have drag, and we have to have a thrust because of drag. So it's the force that the engines make on the airplane and make it move forward. So the first thing I'll explain is drag. So we can imagine drag. It's kind of intuitive. It's the same thing as is happening here. Someone trying to walk in this very wind, and the wind tries to push the person backwards, and then the person has to do some force, which would be the engines of the airplane in this case, and this would be the thrust. So this is drag. And what is lift? Lift is a bit more difficult because in the end, we need to explain how airplane stays lifted. And to explain this, I will come back to buoyant force that I just explained. And I explained this using the formula that is like density times volume times gravity. But here I will use another approach. So we see that we have a pressure in this object underwater and a lower pressure in the top. And actually, the force in each one of those two sides is pressure times area. So what happens is that we have a greater pressure in the bottom that tries to push the object up, and a lower pressure in the top. So this difference of pressure times area also can be a formula to say how this buoyant force works. And this is basically what's happening in the airplane. So this is a cut of the wings. So we call this shape an airfoil. And this is the shape of the wings on the airplane. And those wings are designed in the way that we have a lower pressure in the top and a higher pressure in the bottom. And this lower, like this higher pressure minus the lower pressure, is what causes the airplanes to stay in the sky. So it's this difference of pressure between the top of the bottom in the airplane. There's different ways of saying why this happens. The easiest one would just say that we have like the streams like of air here have a higher velocity and in the bottom has a lower velocity, and this generates the difference of pressure. So this happens because this is a very good shape and it works. And we can also see drag from this thing. What happens is that the force that the wings generate are actually this direction here. So we have lift, which would be like the force that is making in the vertical. But we also have a bit of drag. So the best shapes are those that generate more lift for less drag. It's impossible not to have drag, but we can minimize it. And to calculate it, we just need to know the shape and the angle of attack. A different angle can also cause different lifts and drags. And just as an illustration of that, I have like a flat plane here and a nice shape that we see on wings nowadays. And just as curiosity, Wright brothers airplane actually use this flat plane thing. And it can generate lift if you have some angle. But the problem with those flat wings is that it generates more drag compared to this one. So we need more fuel for those flat wings. And this is not nice. We want to have less fuel as possible being used. So how do airplanes fly? It's because the difference of pressure between the top and the bottom of the wings generate the necessary lift that we need for them to fly. And here we come to a very last question. How does time only move forward? And this is something that we know intuitively. Like, we cannot go back to the past. We cannot like just clean up our messes that we did like days, years, months ago. But we can move forward. And why is that? I'll just start saying, actually, before even this picture, is that this is an open unanswer question in physics. So I'll give you now, not probably the right one, but the best one that we can give right now. And I'll just start saying that if you've ever heard of general relativity, you know that we have space-time and time acts as a dimension. So I'll start talking about the space dimensions, the ones that we know. Like I can move to one side, from one side to the other. We can move like my front and to my back. And I can even move up and down. It's kind of hard with gravity, but the problem is gravity. So we can move in space like in all directions. That's okay. But we cannot move in time. Like we know we can go to the future, but the past, it's not achievable. And you may think, oh, okay, maybe there's like something in the equations that we have in mechanics. So like I just wrote here kinematic equations, and we see that we have velocity. This is also velocity, acceleration, time. This is distance. And okay, these are the equations. The thing is, we can have positive and negative velocities. So positive velocities is when we have the velocity pointing to the positive axis. Negative velocity is when it's pointing to the negative axis. I haven't make a drawing here, but we can also have positive and negative displacements and positive and negative accelerations. But this equation doesn't say anything about if you can or cannot have time moving backwards. And from those equations, we can. It's not impossible. I just need to write here negative times, and it would work. So why times cannot move backwards? You may be tempted to think there's something in general relativity, but there's not. Or maybe quantum mechanics, but again, nothing there. The only place that we have in physics that says time has to move forward is thermodynamics, specifically second law. So if you ever heard of second law of thermodynamics, it says that heat passes from hotter to colder objects. And it only does the opposite direction if we give energy to the system. So this is how we learn it in school. But there's a nice thing about this second law, is that we can define a quantity called entropy. And there's a second way of defining this law, is that entropy in the universe, entropy in not in this, like, any event that happens has to be greater or equal than 0. So this basically means that if something happens, entropy has to increase. So entropy in the universe has always been increasing for as long as the universe exists. And entropy cannot decrease. And this is what, for us, the best answer for our time is what blocks time moving forward. We cannot have decreasing entropy. But you may ask, what is entropy? So I have this example here just to show you. So this would be a low entropy system, and this is a high entropy system. I don't know whether there's a V here, so we just forget if you saw this V. It's not there. And we see that here we have like milk and coffee, and it's not mixed together. So we have less possibilities of putting those milk and coffee particles together so they don't mix. It's like not only a low entropy state, but it's a low probability state. Like we have less possible ways that we can just mix together those two things. So if you want milk and coffee to be together, the only thing we can do is just changing those things and those things, but we cannot mix between them. And when we increase entropy, we are also increasing the amount of things that we can do with the system. So we have more possibilities, of changing it, and then we change the entropy. And we know, like by our daily lives, if we mix coffee and milk, they do not will mix. So this is what blocks time. And we have several other examples. So when you crack an egg, you break a glass, or you do anything in your life, you're increasing entropy of the universe. And this makes the arrow of time always move forward. So this is our last question. Entropy causes the time to move forward, and as I said, it's the best explanation that we can get with physics right now. Maybe 50, 100 years from now, we'll have a breakthrough in physics, and this answer will just change. But for now, this is what we can say. So this finishes our talk for today. I really hope you enjoyed, you have learned something. And the next talk that we'll have will be October 15, and will be about the sounds of space. And if you have any questions, we still have a few minutes before 2, so maybe we start like taking things off here, but you ask. Okay, no questions. So I hope you have liked it. And
we have one question.
Okay.
You had mentioned dark matter previously. Is that what are we talking about when you talk about dark matter? Is that something you can hold in your hand, or is it, like, what is it?
So we exactly don't know what it is. We can't see it. Like it doesn't interact electromagnetically. We can only measure its mass like objects move around something which we can't see. And since we can't see, it's dark. But what constitutes dark matter, it's an open problem. Because it doesn't interact with anything other than gravity. And gravity is very, very weak. So that's the problem. But yeah, we should definitely have a talk about dark matter sometime next semester. Yeah. Any more questions, comments, concerns? Okay.
Thank you.
Thank you, everyone. Thanks for coming.